guys, welcome to a brand new series. Here we will be covering the craziness of quantum mechanics, starting from the creation of quantum mechanics to where it's at now. I'll be explaining each and every phenomena and the physicists who contributed to get quantum mechanics to where it is today. You'll find that the mathematics in this will get a little harder as we go through the series, but don't worry, I'll be explaining this all to you as we go through it. So today we're going to be covering in part 1 the brief history of the creation of quantum mechanics. What is quantum mechanics and why is it so useful? So quantum mechanics provides us with a theoretical framework which makes it possible to describe with reasonably good accuracy the behavior of radiation and matter at microscopic scales. Not to put it small, but the creation of quantum mechanics is the most outstanding development in modern science. It's almost like a revolution that's changed the old concepts of reality in many, many different ways. For instance, we've got a mathematician here called Henri Poincare who has said that it is hardly necessary to point out how much quantum theory deviates from everything that one has imagined until now. It is, without doubt, the greatest and deepest revolution to which natural philosophy has been subjected since Newton. So in a nutshell, Newton's discovery of gravity and much of his other findings were groundbreaking in physics, and the creation of quantum mechanics is arguably on par with those findings. Towards the end of the 19th century, physicists had started believing that the fundamental laws of physics had been all discovered, meaning that a lot of the main task of physics was over, and that various branches of physics were unified in a general theoretical framework, now called classical physics. So the universe consists of two types of entities: radiation and matter. Classical mechanics was formulated by Newton and further developed by Hamilton, Lagrange and many others. Maxwell, another scientist, developed the theory of electromagnetic theory in 1855. You might actually be studying this in your university or A-level physics courses. To briefly mention it, Maxwell combined electricity, magnetism and optics into a single framework. He showed that all radiation, including light, are electromagnetic waves. However, it wasn't until 1887 that this was experimentally confirmed by Hertz, and it seemed that all waves showed the interference and diffraction phenomena, which were well understood theoretically. During the end of the 19th century and the beginning of the 20th, physicists turned their attention to the study of microscopic structure of matter, the nature of electromagnetic radiation, and the interaction of radiation with matter, and the outcome could not be explained on the basis of classical physics. This puzzled a lot of theoretical physicists. Quantum theory had its origin in the attempts made to explain these results. So radical new concepts were required, which meant that it was completely incompatible with classical physics. These new concepts were the particle nature of radiation, the wave nature of matter, and the quantization of physical quantities. We'll get into these a little later on. Moving on, the quantum revolution. The quantum revolution was started by Max Planck in the year 1900, discovering the equation which accounted for the spectral distribution of energy in radiation emitted by a black body. Planck was 42 and a very, very deeply conservative person, so he wasn't really open to new ideas. Even Planck said himself, "What I did can be described as an act of desperation." Planck later struggled hopelessly to get rid of the quantum hypothesis, however much he tried. He and most physicists believed that the introduction of quantum physics was just a mathematical trick to get the right equation, and it didn't really have any physical significance. However, as we know, that was not to be. An unknown 26-year-old clerk in the patent office in Switzerland realized the significance of Planck's work. He was the genius that is Albert Einstein. After reading Planck's work, Einstein felt shocked and baffled. He felt as if the ground had been pulled from under one, with no firm foundation to be seen anywhere upon which one could have built it. Even though Einstein felt like this, he went one step further. Planck had not actually quantized radiation, so he simply said that the radiating energy was absorbed or emitted by matter in discrete lumps, called quanta. However, he believed that the radiation itself was a continuous wave phenomenon. Einstein made the most revolutionary suggestion. He said that the electromagnetic radiation was propagated in the form of quanta. These quanta, as we know now, are called photons. He applied the photon hypothesis to explain the photoelectric effect. The photoelectric effect and the equation is one of the most beautiful, elegant and simple systems in physics. To put it simply, light is shone onto a bit of metal. The metal then emits electrons, or photoelectrons, which then travel around the circuit and power whatever connected to it. I'll explain more of this as we go through the videos. In 1905, Einstein sent the paper to Annalen der Physik. Planck was actually the advisor for the journal. Even though he completely disagreed with Einstein's quantum of light, Planck allowed the paper to be published. However, for the next 10 years, No other physicists believed in the quantum of light. The next important step in the development of quantum theory was taken by Niels Bohr in 1913. However, before that, Ernst Rutherford had proposed the nuclear model of the atom. However, this model could not be stable, according to a classical electromagnetic theory. Bohr was struggling to save the nuclear atom, because from various considerations he was convinced that the nuclear atom was indeed stable and the fault lies with classical physics, which predicted its collapse. He quickly realized that to save Rutherford's atom, some radical change was required. First of all, he quantized electron orbits, arguing that an electron in an atom could occupy some orbits. This he called stationary states. This was crucial, and Bohr was a genius. He had actually developed the first successful theory explaining the spectra of hydrogen-like atoms. Alright guys, so that'll be it from me today. I hope you enjoyed and took something from this video. I'd love to share my passion for and knowledge of physics with you guys. So this video will be a two-parter. The next video will be up next week, so stay tuned for that. But for now, that's it from me. I hope you guys enjoyed, and I'll see you all later. Bye!